Good day, ladies and gentlemen. My name is Kushimo, and I'll be talking to you about the advanced metering infrastructure, which features IoT payments functionality. In the next few minutes, I would introduce the advanced metering infrastructure and the reason why it is a better alternative to the traditional meters. I would talk about the theory it was built on and explain the method we've used to build the advanced metering infrastructure and why our advanced metering infrastructure is different from the generally known advanced metering infrastructure. I would also show the results of our research, and I would talk about the limitations that the model we've built has. Metering is an important part of energy distribution as it helps both the distribution company and the customers. It prevents billing irregularities and unpaid bills. There are a few technologies that have been used for metering. Some of them are the mechanical meters, the simple digital meters, the remotely read meters, prepaid meters, and the advanced metering infrastructure. Some of these are traditional methods which come with some limitations. Example is sometimes the customers have to wait till the end of the month before they can know how much they've consumed. The accuracy of these traditional meters could be questioned. The dynamics of the system does not lend itself to hourly tariffs, and payment is expensive and time consuming. This brings the need to opt for the advanced metering infrastructure because it cuts these limitations. The advanced metering infrastructure is a device that records information such as consumption of electric energy, voltage levels, current levels. It records power factor, and this information are communicated to the consumers for greater clarity, and also the electricity suppliers for system monitoring and customer billing. You can think of an advanced metering infrastructure as a web of smart meters combined in a network or connected together in a network, showing customers what they are using and how much they need to pay and the tariff that they're using. It also shows the distribution company or the supplier how much each user is using at that moment in time. Everything connected together on the cloud. For our energy meter, for our advanced metering infrastructure, we are going to be measuring 300 volts DC, and we measure the current, the voltage level, and the energy consumed and the energy remaining based on how much you bought. We are implementing the energy purchase functionality and real-time monitoring of power consumption, energy balance on site and remotely. The advanced metering infrastructure is set up to monitor energy usage and availability of energy. For this, we need to measure the voltage supplied and the current being drawn by the load. We need to compute these values using a microcontroller and upload them to the cloud platform from where we can send all that data to the consumer. In our implementation, we've selected the ACS712 all effect current sensor, and we use the node MCU microcontroller, which is ESP8266 based. Most advanced metering infrastructures have been built to take in alternating current supply. Our method of the advanced metering infrastructure takes in 300 volts DC supply and connects it to the load. The current is measured, like I said, using the ACS712 current sensor, and the node MCU is the microcontroller that we're going to be using to compute these values and upload them to the database, as the node MCU carries a Wi-Fi module along with it. We've selected a Wi-Fi module instead of a GSM module because we encourage the use of Wi-Fi and smart devices in our microgrid, because this project is based on the advanced monitoring infrastructure within a smart microgrid. So there are other devices that will be using an internet connection, and it would be cost effective if all those devices are connected to the same network. That is why we're opting for a Wi-Fi module instead of a GSM module. Now the microcontroller sends those data to Google Firebase. We are taking Google Firebase as our database to store those data, and the data can be accessed via a web app or an Android application which we have created. The MCU microcontroller has the disadvantage of having fewer analog inputs. So we have implemented the MCP3008 analog to digital converter extender for more analog inputs. We have an LCD for on-site monitoring of the meter, and of course you can monitor the meter remotely via the web app and the Android application. How do we measure the 300 volt DC? We've used the voltage is measured by a series connection of Zener diodes and resistors to chop up the voltage to a we've chopped up the voltage to an acceptable voltage by the microcontroller, so it can read the values appropriately and within its limits. This is a block diagram showing how the connection has been made. This is the AMI circuit connection representation on Proteus. This is the 300 volts supply that goes directly to the Zener diode in series connection. These Zener diodes chop off the voltage up until the point where it gets to a level that it can pass through a voltage divider and then go directly to the node MCU and be in the limits of the node MCU. Also, we have this connection going directly to the current sensor to monitor the current readings, or the effect current sensor to check the current readings and send them to the node MCU microcontroller. The node MCU microcontroller calculates the power, the instantaneous power, and also calculates the energy over the time of the recordings. It then sends this data to the online database, calculates the energy, retrieves the energy availability, and if there's energy available, it makes sure that the relays are on and the supply is connected to the load. If the node MCU picks up information from the database that the energy available is 0, it will disconnect these relays, and therefore the supply will be disconnected from the load. Also, we have an LCD display which takes all this information and displays it to the user on site. On the right hand side, we have our device being tested, and on the left is a table where we tested the current readings of our AMI and compared it with a fluke meter current reading. On no load, we had 0 amps. We had 0 amps on both readings. When we used a 60-watt bulb as a load, on the fluke meter we had 0.4 amps. On the AMI we had 0.5 amps. We increased that to an 100-watt bulb and we had 0.9 amps on the fluke meter and 1.06 amps on the AMI current reading. We increased that to a 200 watt bulb, and we had 1.8 amps on our float meter, 1.9 amps on our AMI. When we used a combination of 160 watt bulb, we had 1.40 amperes on the float meter and 1.57 amperes on the AMI. This shows that compared to the float meter, we have an accuracy of 88.23%. This is our web app and is going to be available to the distribution company to monitor users. For our prototype, we have two users, user 1 and user 2. You can monitor the voltage, the current, the instantaneous power, the energy used over time, and the energy available to that user. Assuming the user calls in to load more energy, you can accept payments from the distribution company and add that amount of energy to what is already available here. Now, the advanced metering infrastructure can cater for as many users as possible, and this is scalable to our web app is also scalable to a large amount of users. Now, all this information is being gotten from the Google Firebase, like I said. The Google Firebase stores its data in JSON and uploads it in real time. So this is how the information is stored on the database, and this is our AMI in action. We added a load, the 60 watts bulb, and this is the current reading, voltage reading, instantaneous power, energy used, and energy available. Increasing that load shows more current has been drawn, and it is also updated on our AMI. This is just a demonstration to show how the current is increasing and the energy is consumed faster once you increase the load. This is a demonstration of the monitoring being done by our mobile application. So the application has the functionality of monitoring your data and also paying for data. You monitor the data in real time, so the values that you can see on your meter is being updated on the application. This is a demonstration of how payments can be made using our AMI. For this, we use the Paystack APK and Paystack online platform for payments. We've used a demo account, so we are not using actual values of our ATM card. Now, when you input the amount of data you wish to buy, it converts it to energy, and once you press enter, you have payment. It validates the payment and confirms it, and increases the value of your energy on both the web app and the device itself. This shows how once you turn off the load, how the data updates it on the AMI. Limitations to this device: the product is heavily reliant on IoT and requires working internet connection. It does not function effectively in remote areas with poor internet access. The product uses rechargeable batteries that will require replacement after an estimated period of time, or 500 full charge cycles. The application currently works for Android users only. It does not work on the iOS platform and the Windows platform. This AMI is specifically designed for devices that work with 300 volts supply voltage.